Okay. So so you have this. So what I had written is P of something. Let's say R n or x n, right? X n is equal to x times n. So it goes like exponential of n times phi of x, right? And phi of x has some expression, right? So what I say that this function will look something like this, right? So I don't know the exact form here, but it will look something like this, right? So this need not be 0. In this case, let's say this is equal to p minus q, right? So now, so there is a factor n here, right? So then this whole thing actually goes down very fast, right? So it goes down when x becomes, this range becomes, let's say, of order 1 over n, right? But now you have to find out the maximum of this function. So how do you find the maximum? So you take a derivative, because near the maximum the slope is 0, right? So you take a derivative and you find out phi prime x is equal to 0, x, let's say star, this is x star equal to p minus q, right? This is equal to 0. So you find the maximum, and then, so what is the maximum? How do you know it is a maximum? You find the derivative is equal to 0, but how do you know that it's a maximum? So you calculate the second derivative, right? So it calculate the second derivative, and second derivative should be negative, right? So then how does this function behave near that x0? Huh? So how does this function, how should it behave near x star? If the first derivative is 0 and second derivative has some value, right? So how should it behave, right? So this phi of x should be something like, so minus phi x star, whatever this thing, x minus x star whole square, right? So this function, if you take the first derivative plus these higher order terms, right? So there cannot be any this power of 1, because if there is a power of 1, then this first derivative will not be 0. So this is how this function should behave, right? So now you have to find out what is phi's double derivative at that point, and that you have found, and that is equal to, right? So then this is your form, right? So you have to find this thing, and that will be your whatever 1 over 4 pq. Okay. So yesterday we talked about this Brownian motion, right? So what we did yesterday, so we talked about Brownian motion. Right? And in the Brownian motion we showed that the diffusion coefficient is related to some parameters of the medium, right? So we showed the diffusion coefficient is equal to Kb times the temperature times the gamma. So where gamma is a friction coefficient, and if you have a spherical ball, then it is given by 6 pi eta times r, and I think is going to derive this, right? Okay. So now, so this is where we stopped yesterday. So here is the diffusion coefficient in terms of the parameters of the medium, right? This is the what is the temperature of the medium and what is the friction coefficient of the medium, right? So today what we are going to do, so we are going to obtain this diffusion coefficient in terms of the microscopic fluctuation of the particle, right? So now we will just look at the particle and obtain an expression for this diffusion coefficient in terms of that, right? So let's call it D in terms of microscopic fluctuation. Right, so this is what we are going to do. So let's, right. So yesterday when we obtained this current, we said there is a diffusion current. So now, so yesterday we put a field, right, to obtain this relation, but this is valid whether the field is there or not there, right. So this we put the field just to obtain this equation, right, but this relation is valid independent of there is a field or not, right. So now we are going to remove the field, right. So we are just going to look at the free diffusion, right. So when you look at a free diffusion, so there is a diffusion current, right. So if you have lots of particle, now imagine that you have lots of particle, so they diffuse, right. It need not be Brownian particle, it can be any particle. For example, if you just put a gas here, lots of gas here, they will diffuse, right. So this is a very particular kind of diffusion where diffusion coefficient is given by that, but in other case it will be something else, right. So what is the current, diffusion current? So this is equal to, so this we have already used yesterday, right. What is this? So it should be proportional to the density gradient, right. So this is equal to minus d times del rho times del t. So this is known as the fixed first law, right. So this, yeah, this is a fixed first law and it has been proposed much before whatever Einstein equation, right. So this is something 1800 something, right. So this is some phenomenological law. It says that, okay, if you have a density gradient, the things flow from the high density to the low density, and therefore there is a current, and the current is proportional to the density gradient to the lowest order, and there is a proportionality constant which is called the diffusion constant, right. So second is, again we have seen in this class that if there is no sink or source, right, so then the particle number must be conserved, right. So then this conservation of the particle number or particle density gives a relation which is called the continuity equation, right. So this was also derived in this class. So this is equal to, what is the continuity equation? So that should be divergence of this. So I will just do it in the one dimension, but you can just generalize to higher dimension. It's very trivial, right. So this is, so in one dimension this is the divergence, right. So this is the continuity equation. So if I now use this and this, so what do I get? So I can just put this thing here. So del x of minus del rho del x, right. So then I get a relation which is del rho del t is equal to del square rho del x square, right. So this is called the diffusion equation or fixed second law, right. So this equation is valid for any diffusion. It need not be Brownian motion, because we saw that yesterday even for random walk, when you took the continuum limit, we obtained the same equation, right. So any diffusion, this equation is valid, okay. So now if you have Brownian particles, lots of Brownian particles, and these are non-interacting, right? So if you have a dilute gas, you can treat them almost like non-interacting. Non-interacting means they don't see each other, right? So then the density is equivalent to probability density, right? Is this statement clear? So density you define for lots of particles, right? This is a particle density, right? So probability density you define for one particle, right? So up to some factor, this density is basically equivalent to the probability density. So is this statement clear to everybody? Right? Okay. So how are you going to measure a density? So what is a density? What is a particle density? What is rho? Huh? No, what is this quantity rho? Rho of x at time t. This quantity rho x at time t. So what is this quantity? What does it mean? So if I consider a small volume around x, right? So this times dx, so this gives me the number of particles in that volume, right? So now imagine you are doing two experiments. So let's do the experiment again in one dimension, but you can do it in any dimension, right? So how are you? So imagine that you are this one dimensional line and you are just making this line in, binning it in delta x, right? So you're just making it this, right? You have bin, and let's say this is your origin somewhere here, right? So how are you going to measure this quantity? So initially you will release n particle here, so you'll just leave n particle here and then let them evolve up to time t. So what will happen after time t? So there will be some particle here, 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 some particle here, and so on, right? So now if you want to find out this quantity at x, so you'll just find out how many, for example, this is x, so you'll just find out how many particles are here, right? And divided by delta x. So this will give you the density, that's the definition of density, right? So now you want to calculate this object. So this is the probability of finding a particle at position x at time t, right? Between x and x plus dx at time t, right? So how are you going to do this experiment? So what I will do, I have the same setup, right? So I will just take only one particle, release at the origin, wait for time t, and find out where is the particle. So here is the particle. So I have a bin here. I'll just put a +1 there, right? So this time this particle is here. So I have a piece of paper where I'll write down the number. So okay, this time I got the particle here. I'll just put a +1 here. So next time again I'll release a particle from here, do the same experiment, wait for time t, and this time the particle will be somewhere, let's say here. So I'll put a +1 here in that whatever spreadsheet I have for that position, right? And I will keep on doing that, right? So I'll do lots of time, let's say r times I'll do. So now to obtain this quantity, this is a probability. So what will happen? So at the end I will have lots of +1 here, lots of, so I will have some numbers here, n, let's say n0, n1, n2, n3, n4, and so on. So these are the, if I add all these ones, I will get those numbers, right? So I will take these numbers divided by r, because r is the number of realization I am doing that experiment, right? So this will give me this object, and I will divide it by n r, right? So this one is normalized, but this one if I just integrate over it, it will give me n, but this is just a factor of n, right? So if I just put a factor of n here, this equation doesn't change, right? So therefore this equation I can also replace by del P del T is equal to del, right, because whether I release all the particles at one go or I release them one by one, it does not matter because they do not interact with each other, right. So therefore these two quantities are equivalent, and therefore this equation, from this equation I can get this equation, right. It is not valid for interacting system, right. Yeah. Yeah. So this is what I have. If you take n particle, n interacting system, then I will have some, I have to write down the density, see, so if I have n interacting particle, if I release them at one go, so it will have some probability distribution, right. So I release n interacting particle once, I will again release n interacting particle another time, I will have some probability distribution, I will have some joint distribution. So that joint distribution will not same as like if I just release particle one by one, and just whatever I will have this marginal and just write as a product of that one, right. Right, because I'll, yeah, so it will have some other equation, right. For example, this particle, they there's some Coulomb force between them or something, right. So I will not get this equation then, right. Yeah. Okay. So this is fine, but this equation I just got from just arguing that this and this P and rho, they are similar, so that's why I got this one. But I am also going to derive this equation, right, starting from the whatever I know about the system, right. So in fact I did a derivation yesterday for the random walk, so this derivation will be very similar. Okay. So what I am going to do, so let's look at this one. So this is my time t, and this is my position x, and let's consider a trajectory. So it goes from here and it will be something like that, right. So now I want to find out what is the probability here, right, at time, let's say t plus delta t. So I say the probability that it is at x at t plus delta t. So it is exactly the same derivation yesterday, which one I have done yesterday. So this is equal to, this particle must come somewhere from the neighbor inside, right. So it must be somewhere before. So this is same as probability that particle was at position x minus delta x at time t. Then this delta x can be anything, right. So yesterday it was just the nearest neighbor, but it is a continuous space, it can come from any space. So there is a probability of the jump in delta t of delta x, and then I have to integrate over all delta x, right. This I can do because the system is Markovian, right. So the probability at one instant, it just depends on the probability of a previous instant, not full histories, right. So in general it could have been that this probability, it depends on full history, right. So that is not a Markovian system, right. So here I can do because it just depends on the previous instant. So now what I will do, I will just do the same thing I did yesterday. So I will just expand in Taylor series, right. So what is the Taylor series of this? So this is P of xt minus delta x del P del x plus delta x square by 2 del 2P del x square, so on. And this also I will just expand in Taylor series, P of xt plus delta t del P del t plus 1, right. So if I do that, this phi is again a probability density, right. So it must be normalized, right. So it means that phi of delta t delta x d of delta x minus infinity plus infinity, this must be equal to 1, right. So therefore for the first time it just comes out, right. So this gives me, this is equal to P of xt, right. What about the second term? this phi also must be symmetric, right? There is no reason that something comes from the left more often than from the right, because there is no external field in the system, right? There is no bias, it's a homogeneous system, right? So this object, so delta x times phi times this one, integrate over it, that is the first moment, right? So this is a symmetric function, this is a anti-symmetric function, so the integral must be 0, right? So therefore there is no second term, and then I have a third term. What is the third term? So third term is delta x square by 2 phi of delta t delta x d of delta x times del square p del x square, right? So see that this is independent of delta x, right? So delta x is only here. So this is a function of p is a function of now x, not delta x, right? So I have only this term, right? So what is this term? So this term, so this object cancel to this object, and I must get this equation, right? So if I want to get this equation, what should I put for this one? So I must get this equation, right? So I argued that this is the equation for the system. So what should I put for this one? Right? This is delta t, del p, del t, right? So this I have to put d, right? If I put this is d, then this is same as this equation, d delta t, right? This is same as that equation. So therefore I have a definition of d, right? So what is the definition of d I must use? So I have to use that d is equal to 1 by 2 delta t, so this 2 I took it outside, minus infinity to plus infinity delta x square phi of delta x in time delta t d delta x. Now what is this object? This is just the expectation value of this one, right? So therefore this is equal to delta x square expectation value divided by 2 delta t, right? So now I have two definition of d. So this is one definition, and this other definition is d is equal to delta x square average by 2, right? So in fact this is a general definition again. So this need not be for Brownian motion, because I didn't use anything about the Brownian motion while deriving this expression of d, right? So this is the expression d basically given in terms of the microscopic fluctuations. Yeah, so now it depends on, see, so what kind of memory you have, right? So I will not have time to work with finite memory, but it depends on what kind of memory you have. If it is an exponential memory, right? So then what you can do, you can actually go in one dimensional higher, right? Again define a Markovian system, right? This Fokker-Planck equation, the way you derive this Fokker-Planck equation is only valid for Markovian system, right? For non-Markovian system you don't have a Fokker-Planck equation, right? Because you see that the way I derive, you need this Markovian property. But if you have, let's say your noise has a memory which is exponentially correlated, right? So then you can go one step higher and define a dynamics for the noise, right? So you include this noise also in your variable, and there will be a dynamics for the noise, because how do you get an exponential, right? The exponential you get from a first order differential equation, so you can just write down a first order differential equation for the noise, right? So then this whatever your original variable plus the noise variable, so they define a Markovian system, and you can write down a Fokker-Planck equation for that system. But if you have any general noise, for example power law correlated noise, you cannot write down a Fokker-Planck equation for that. Okay, so this is what I got. Yeah. Yeah. So to obtain this one, so one I use that J is equal to minus d del rho del x, and the other one I just use the continuity equation, right? Because particle must not vanish or created, right? Diffusion coefficient is constant over the so when diffusion coefficient is not constant, then it is more complicated, but then one can again write down those equations, right? So now, so maybe I will just derive the general Fokker-Planck equation for any d, but then when diffusion coefficient is not constant, you have to be also careful. So this equation will be valid, but you have to be careful how you calculate these averages when there is diffusion coefficient. See here this is just d, but there when you evaluate these averages you have to be more careful. Okay. This one? Yeah. Because this one, so what is that term? So that term is integral del x phi of del x d delta x minus infinity to plus infinity. So this is a symmetric function, delta x goes to minus delta x, this is same. This gives a negative sign if delta x goes to minus delta x, right? So the whole integrand is antisymmetric, right? So therefore this it must be vanished, right? Del p del x is there, but if the del p del x is independent of delta x. Del p del x, these objects, these are independent of delta x. These are just the position, depends on the position, independent of the jump distribution. These derivatives are with respect to x, not with respect to delta x. Imagine delta x is another variable, call it z, right? So delta x is, you call it z or something, right? So these are independent variables. Because I know that in the system it is homogeneous, so there is a, so I'll come when phi is not symmetric. But in this case, what is this system? You have a beaker, you have a particle there. What is the reason that phi is not symmetric? The particle coming from the left should be, the probability of particle coming from the left should be same as the probability of particle coming from the right, right? Because your system is homogeneous. If you have an external field, so then this term will be there, and then your equation will have another term, and that term was that term we got for when you derive this random walk with a p and q, right? So there is one more term. If you remember, so we had this term minus d mu del p del x, right? So that was a case of constant field, but you can write down an equation for any arbitrary field, and I will probably do today. Yeah. Yeah. This is the odd order will be vanished, and this even order will go to 0 when delta t goes to 0. It is the same argument I gave yesterday for the random walk, right? Because you have to look at what is the order of this term, right? This order is delta t. So then what will be the order of the next term, right? And then if you divide it by delta t, and in the limit delta t goes to 0, that term will vanish. It's the same argument for the random walk I gave yesterday, right? Yeah. D can be T no, this because 1 minute. See, this had only information. This current I wrote down. It has only information about the space, right? Yeah. So otherwise, I should write down something like J at x and t. Okay, so that I can still call it minus d del rho del x and del rho x t del t is equal to minus del x of j at x and t. I guess it's still valid. Yeah. Yeah, so it can be a function of t. Yeah, so it can be still valid. Yeah. But yeah, when it is a function, so I'll come to it. When it's a function of x and t, one has to be careful how you put or where you put, basically. Yeah. Okay, so this is what I got. So these are the two equations I get. So this is in the limit. So I should write this is equal to this. D is equal to limit delta t goes to 0, delta x square divided by 2 delta t. So these are the two definition of diffusion coefficient I have. And so I'll give you an exercise now. So using this result and the fact that delta x at different times are independent, right? So they don't, delta x at two different times, they are independent of each other. And use this fact, show that x minus x0, xt minus x0. So this is a position at time t, this is a position at time 0, whole square average is equal to 2dt. So using this equation and the fact that delta x at different times are uncorrelated, right? So that this is equal to that. Yeah. So now I have a diffusion equation and I know the answer. What is the answer? Because we got the answer for the random walk case for this equation yesterday. So it's a Gaussian. So you verified that is the answer yesterday, but how do you derive this answer, right? So let's see how to derive this answer. Yeah. So now, okay, it's a very good question. Now you have these two definitions of diffusion coefficient. What do you do with that, right? So what you can do, so you can, what is Kb in terms of the gas constant? R by Na, okay? Yes, I was supposed to mention that, but I didn't, so it is a very good question. So Kb is R by Na. So D is equal to R by Na times T. And if I have a spherical ball, what is gamma? 6 pi eta R. And I said that this is the definition of diffusion coefficient. But then I have given you an exercise to show that this is even true for any delta t. It need not be 0. It need not be the limit delta t goes to 0, right? So therefore, I can also write this as xt minus x0 whole square expectation value of this divided by 2 t, right? So that was the exercise, right? Xt minus x0. So it just says that this delta x is now xt minus x0. So this is valid for any delta t. It need not be small, right? So then d is just this one. So now this is temperature. It's very easy to measure, right? Viscosity is easy to measure. Radius of the particle. How big are these particles? Micron size, but you can measure, right? If you look at in a microscope, you can just measure the radius of the particle. And so you can observe this particle in under the microscope. So you look at from some position and just look at how much it displays. So what will happen? So in fact, this is in one dimension, but this will be true in any dimension. Or you can just project the one dimension, project it to one dimension. So you have this delta x in some time c. So you can measure this one. So you just do measure lots of experiments, right? Square it, take the average over that, divide it by t. So this right hand side you can measure. So left hand side you can measure t, you can measure eta, you can measure r, these are, and this gas constant is known by other measurement very accurately. So therefore, what is remaining? The Avogadro's number. So you can use this relation to actually measure the Avogadro's number, and this is what Jean Perrat did, and he got a Nobel Prize for this one, right? In 1925 or something like that. Yeah. Huh? 27. Huh? No. The Nobel Prize was in 1925 or 1927 or something like that. Yeah. Yeah. Yeah.
Comment is the following, that this equation dp dt equal to capital T dt dx squared. When I came late, maybe
Yeah.
you derive it from the random walk problem.
Yeah.
By going to the configuration.
Yeah.
So there is very nice articles like Narasimhan, physics today and current science also,
Yeah.
1909, 1910. Where he makes a distinction between what he calls physical diffusion and stochastic diffusion. So the random walk problem
Will be still diffusive at some point, because some convection here is uncorrelated to the convection somewhere there, right? So the motion will still be diffusive, but it will not be Brownian motion, right? So therefore, to measure this one, you have to take actually extra precaution. What people do, you just take a very small drop and put a microfilm on top of that, so that there is no evaporation. You don't take a big beaker of water and try to measure the diffusion coefficient. Then what will happen? There will be temperature inefficiencies. Because of that, again there will be convection, right? And those will not give you the right result. It will be still diffusion, right? If you measure this xt minus x0 square, it will still go like t, right? Because it is diffusion, but it will not Brownian motion. So there is a clear distinction between a Brownian motion and a diffusion. Brownian motion, a kind of diffusion, right? Okay. So so now, so it is about the. So what is the solution of this equation? So last time we saw that this expression. So I am just writing now. 0 is equal to 4 pi dt exponential of minus x minus x0 whole square by 4 dt. So we saw that this is a solution of this equation. So you just, instead of p, if you just put z here, this is a solution of this equation with the initial condition that if t goes to 0, what happened to this one, this function? It becomes a delta function, right? Because if x is not equal to x0, if it is e power minus something by infinity, it goes to 0, right? So with the initial condition, p of x0 is equal to delta x minus x0, right? So this is the solution of the diffusion equation. If you start from the, imagine that at the time 0, the particle is at the origin, So you ask what is the probability that you will find the particle at position x at time t. So this is the solution because we showed yesterday, right, for the Brownian random walk case. Okay. So now, so what is the general solution? Suppose initially instead of this one you have some general p of x0. So I am going to claim that the general solution is equal to dx0 p of x0 at 0 and g of xt x0 0, right. So this is the general solution for this equation, right. So if you take t goes to 0, so this becomes a delta function. So then delta function, it gives basically x at t0 is equal to p of x0 0, right. Yeah. So it gives me, yeah. But this is a general case, and then I am going to show this one, right. Okay. So how do you do? So actually you can do this derivation directly in 3 dimensions, but I will just leave it as a, so it's, there is no difficulty going from 1 dimension to 3 dimension, it's just almost same, okay, but let's do it in 1 dimension. So how do you do? So we talked about something called the characteristic function, right, which is like the Fourier transform. So this is what we are going to do. We are going to multiply by e power ikx on both sides and integrate over x, right. So if you multiply by, so I am going to integrate over x and multiply by e power ikx, that goes from minus infinity to plus infinity, right. So this is a derivative with respect to time, and I am integrating over x, these are independent, right. So I can just change the order, right. So then the left hand side becomes del, so let's call it tilde, this of k and t by del t. So this p tilde is basically this into p of xt, right. So I am going to multiply. What about the right hand side? So right hand side, it's a derivative with respect to x, 2 derivatives in fact, and there is a integral with respect to x. So I cannot interchange the order, but what I can do, I can integrate it by parts, right. So you do integrate by parts 2 times, and what you get is square kt. So you assume that both p probabilities and the its derivative vanishes as x goes to plus infinity and minus infinity, right. So probability must vanish because it's normalized, right. So it vanishes, and the derivative is basically a current, so it also vanishes at plus infinity and minus infinity. So this you should just do it, it is very trivial, you just multiply by this one and just do integral by parts twice, right. So this is how you get rid of this derivative from inside the integral, right. You just integral by, so this is what you get. So now this is easy to solve, right. This is a first order differential equation, and you all know how to solve this one. So what is the answer? So p of kt is equal to, constant is 0 t e power minus d k square t. Sorry, this is t0, k0, sorry. No, what is this? This is k0, right? Yeah. Right, so this is the solution. Is it okay? Right, this is the solution. So now what is this object? pk, huh? So this is just the Fourier transform of Px0. So what is the Fourier transform of Px0? 1 by 2 pi minus infinity to plus infinity d, no, sorry, this is just the characteristic function of, there is no 2 pi, right? So this is just the, this object with p of x0 integral over, so minus infinity to plus infinity dx0 p of x0 0 e power I k x0. So this is this one, right? So this is p of xt, so this is equal to p tilde of k t, right? Huh? That is there, I am not writing it, this is only for this part. So now this is minus d k square t. So this is only function of k and this is only function of x0, right? And you know what is the inverse of this one, right? That we have done, right? If this is a characteristic function of a Gaussian distribution, right? So what is that Gaussian distribution? In fact, that Gaussian distribution is this one, right? So therefore, if I invert this one, p of xt, so what I get? Minus infinity to plus infinity dx0 p of x0 0 g of xt x0 0, right? Right, this is what I get. No, this comes from there, right? You take this guy here, this guy there, you integrate. This is actually this is a differential equation. I can actually write this as a ordinary differential equation. You just forget about k variable here. K is like a constant, right? Because there is no derivative with respect to k. So as far as this equation is concerned, so k is like a parameter. So in fact, what I can write, so d dt of p tilde t is equal to minus some a p tilde t, right? K is just a parameter as far as this equation is concerned. No, how will you get? This term, right? So if you derivative, that will go away, but you have this linear term, right? So it will not be a solution, right? So it must have unique solutions, right? These equations which satisfies proper boundary condition or initial conditions, right? Yeah. Okay, so this is what I get. Again, using this equation or using this equation, you should verify that if you calculate x minus x0 whole square average, you get 2 dt. Right? It's very easy because it will be just given by the variance of this one, right? It's still like a variance of the Gaussian distribution, right? So what is the variance? 2 times 2 dt. So 2 dt is the variance, and this is the variance of this distribution, right? So it's easy to verify that this is what you get. Okay, so now so you can do it. You can again write down the equation. So you see, so let's derive the Langevin equation, and you see how you get a Fokker-Planck equation from a Langevin equation, and you can just put that whatever your force in the Langevin equation, and just get the appropriate Fokker-Planck equation from that, right? Because noise is also like a time-dependent force, right? It's a very particular kind of time-dependent force. But if you have some other kind of time-dependent force, you can just put it there. Yeah. So let's see how you get a Fokker-Planck equation from a Langevin equation, right? Yeah. Okay. So now, so I think you have seen this equation yesterday already, this Langevin equation, but let's try to give a Langevin description of this one. How do you get that? Okay. Okay. So this delta x's are independent, right? They just sometimes it goes to the left or sometimes it goes to the right, right? So if you look at the trajectory of a particle, let's say in delta t, so in delta t, somehow it will go like this, somehow it might go like this, somehow it might go like this, sometimes it might go like this, sometimes it might go like this, and so on, right? So therefore, so these are the slope, right? This is x and this is time, and these are just the delta x's, right? So therefore, this delta x by delta t is a random variable, right? So it goes sometimes, the slopes are random variable, right? So let's call this random variable, see, this is at time t. So what kind of properties this random variable satisfy? Right? So we are going to find the properties of this random variable xi t. So you see that delta x is a Gaussian random variable, right? Because it has a distribution which is Gaussian. That's what we showed, right? So I'm going to use whatever we have done before this one to define the properties of this noise, right? Since delta x is Gaussian, so therefore delta t is also Gaussian, right? So there is, so this is not very important for if you want to just derive a Fokker-Planck equation, but this is important if you want to that the noise actually has a Gaussian form. So if you want to derive a Fokker-Planck equation from a Langevin equation, this statement is not very important. But then if you want to, for example, write down a path integral description of this Brownian motion or diffusion, so then this Gaussian nature is important. Okay. So let's look at what is the average of this noise. So what is the average of delta x? That is 0, right? That's what we saw, because delta x times phi is a symmetric function. So we saw that delta x is equal to 0, so implies delta t at any time this is equal to 0. So delta x at one time and delta x at another time, they are independent, right? So therefore, if I calculate delta t at one time, so this correlation is also equal to 0 if t not equal to t prime, right? Because delta x, so I am just taking this left hand side at two different times, I am just multiplying them, right? So this is equal to 0. So what at the same time, so I just square this one and take the average, right? So if I square this one, what do you get? Delta x square average by delta t square, this is equal to delta t at time t square average, right? I have just taken this one, squared it and took the average. But what is delta x square average by delta t? This is equal to 2d, right? So therefore, this is equal to 2d by delta t, right? So I have a noise whose mean is 0 which is uncorrelated, and at the same time this variance of the noise is 2d times delta t, right. So, when I break into the steps of delta t. So, in fact, this is a very useful definition of the noise, because often if you want to go from the Langevin equation to the Fokker-Planck equation, this is a very useful way of writing down the Langevin equation, okay, or whatever. This is the very useful way of writing down the Langevin equation. But now, okay, you want to write down the usual way. So, you want to write down in the limit delta t going to 0, right. So, in the limit delta t going to 0, okay. So, you want to write down something. So, in the limit delta t going to 0, suppose you just integrate over this noise, what do you get? This goes to what? Delta t goes to 0 when this is still, so let's write down the left hand side. So, left hand side is, there is no problem, right, delta x delta t, limit delta t going to 0, I can just write it this one. So, this one, let me just put it in a code. So, what is the meaning of this delta t going to 0, right? Huh? Which one? This one. So, I am just going to take the delta t going to 0 limit of this one. So, delta x by delta t, limit delta t going to 0 is dx by dt. Yeah, so that is why I put this thing here, right, I put it under code, right. So, I put it there. So, this is basically differentiation from one side, right, but I will come back what is this actually the precise meaning of this delta t going to 0, okay, but this is what you get, right. So, what about the right hand side? So, now right hand side, this will become some noise at time t, and that properties of noise should come from the properties of this noise, right. So, it is basically this noise in the limit delta t going to 0. So, what is the properties of this noise in the limit delta t going to 0? Mean is still 0, they are still uncorrelated if t is not equal to t prime, and what happened to this object? In the limit delta t going to 0, it becomes infinity. But if I integrate this noise, what do I get? So, if I integrate this object delta t t prime, this object dt prime integral over t prime, what do I get? So, I am integrating in the steps of delta t, right. So, it is 0 everywhere except t is t prime. So, this is equal to 2d by delta t times delta t. So, this is equal to 2d. So, you already know what kind of function is this, right. The function is 0 everywhere except one point, and that point it blows up, and if I just integrate the function over all space or whatever time, that the full range of the variable, it gives me something. So, what is that function? So, it is a Dirac delta function. So, therefore, this noise should satisfy. So, I have this equation, this noise should satisfy. So, this is equal to 0, t prime is equal to 2d times delta t minus t prime. So, this equation is called the overdamped Langevin equation, in fact, right. So, this is called the overdamped Langevin equation. So, what is overdamped, right? So, this equation is very different from a Newton's law, right, but this is a classical system, Newton's law must be obeyed, right. This is the only, I mean, equation in some sense, no, for classical mechanics, right. So, what is the Newton's equation? for this particle. Right. So, I am going to explain what is this, the meaning of this overdamp, right. So, this equation, you say that this is the equation, but what about the Newton's equation, right? And Newton equation is the most fundamental equation for classical physics, right? I mean, all particles should follow that equation, no? Rate of change of, what is the Newton equation? d2x dt is equal to the forces. So, what are the forces? So, one is the Dirac force, right. So, this is equal to minus gamma dx dt, and one is the force which you call noise, right. So, this is called, let us call some other term eta of t, right. So, this is what you call, and I am going to put a prefactor here. So, I have told you that either I can use this equation, or I can put the square root of 2d here and define this with a, I can remove this 2d here, right. This is what we, when we went from Gaussian variable of some finite mean and finite variance to a Gaussian variable of 0 mean and unit variance, right. So, you can just, so this is equivalent to, I can just put this square root of 2d here and I can just remove this 2d from here, right. So, this is what I am going to define, but I will not put square root of 2d, I will put something else. So, what I am going to put? I am going to put 2 gamma kbt eta of t. So, I put this factor because I know the answer, but if you do not know the answer, you can just put something, do not put d, but you put something, and from the properties, whatever you are going to see, it should come out automatically, right. Yeah. So, now let us write down in a different way. So, I just divide it by gamma everywhere. So, I have something like m by gamma x dt2 plus dx dt equal to, so in fact let us write down right, dx dt is equal to v, and this is now I divided by gamma. So, gamma is outside, so then if it goes inside, so it is basically 2 kbt by gamma, and 2 kbt by gamma is my diffusion coefficient. So, this is equal to 2d times eta of t, right. So, this is what you have. So, what is the dimension of this? M by gamma. Looking at this equation, can you tell me the dimension of m by gamma? So, it should be time because this is velocity by time, right. This is only velocity, so it has to be time. So, m by gamma has the dimension of time, let us call some time tau, right. So, then I can again write down this equation dv dt plus v by tau is equal to square root of d by tau tau t, right. So, what is the dimension of eta? So, you know the dimension of d, so you should verify that dimension is basically dimension of eta is 1 by square root of time, right. So, you should verify that because you know the other dimensions. So, this equation very easy to solve, right. This is a first order differential equation. So, in fact d dt of e power t by tau v is equal to, let us write it here, by tau plus 2d by tau without t. Right? I just multiply e power t by tau. So this side becomes a perfect derivative, and now I can just integrate this equation, right? And you get something, whatever you get, right? And then you can solve this equation. So I am not going to give the answer, but I am going to yeah.
Okay. So basically, when we are using D as a parameter in this equation,
Yeah.
so before writing the equation, already we are inputting some conditions.
Yeah, because this is how I obtain this one, right?
No, what I am saying is this is a differential equation X.
Yeah.
Okay. And
Which one? This one, right? This one. Yeah.
so basically, and D is having relation delta x square by this.
Yeah.
So doesn't it is a kind of constraint we are imposing to solve the equation? Don't you think this is actually trying the system to do it?
Because I know about the system, right? That's why I cannot put any arbitrary thing there. I know about the system. I have derived what kind of D you should have, and then I have derived what kind of equation you have and what kind of noise property you should have, right? Because this is for the Brownian motion, right? I cannot put any arbitrary diffusion coefficient, right? So it must be related to temperature, viscosity, that's what we derive, and also diffusion coefficient related to the microscopic fluctuation. This is what we have derived, and just using those whatever we have already derived, right? I cannot put something arbitrarily by hand there, right? Yeah. So, okay. So this you can just obtain the what is the velocity at time t. Let me just write it down anyway. So this is equal to v0 e power minus t by tau plus 2d by tau t minus t prime tau dot prime t prime. So this is the velocity you obtain from there, and you can calculate the mean. So mean, when you calculate, I think Susanto has pointed out, this term will go to 0. So mean is just given by this one, so which goes to 0 when t is much larger than tau. You can also calculate the variance, and variance what you obtain is so let me just write a v squared t minus vt square is equal to kbt by m 1 minus e power minus 2t by tau, right? So now, so what you see that if your time is much larger than this tau, right? So if your time is much larger than this tau, so what you get is half m v square is equal to half kbt, right? So this is the reason for putting here. So you could have started with something unknown here and claim that when time is very larger than this sum whatever this microscopic time, you should have this equipartition, right? So that will fix you this one. Okay. So this is basically this time after much larger than this time, the system doesn't remember, the velocity doesn't remember its initial velocities, right? So this is also true from here. So if t is much larger than this time, this velocity doesn't remember its initial velocities, right? So this velocity is equilibrate at this time scale, right? So the velocities of the system equilibrates at the time scale of tau, right? Right? But the position may not equilibrate at the time scale, right? Position will have some other distance. So now if you are looking at a system which is much larger than this time scale, right? So you can drop this term here, right? So this is the meaning of Overdamped equation. So what you can do, actually I am not going to, maybe I will do it in the tutorial. So you can also, now given v, this what is x? So dx dt is equal to vt. So now you have expression for v, so you can write down the expression for x at time t, right? So you can write down the expression for x at time t, and what you can find that if you are looking at a time scale which is much smaller than tau, then your yeah. So let me just. So you can find an expression, you just put it there, and that's this thing. So if you look at a time scale, some delta t which is much smaller than this tau, so what you will find is that delta x square average will go like v0 square average delta t square, right? So what is this average v0? So this is average with respect to the, because velocity is equilibriate, right? So this is basically given by half mv square equal to half kbt. So this is basically kbt by m. So this is ballistic, right? X square goes like t square, means x goes like t. So this is ballistic motion, right? So on the other hand, if you are time t which is much larger than tau, so what you will find is that delta x square goes like. So this is a diffusive behavior, right? So now if you are interested in a time scale which is much larger than tau, so this delta t going to 0 means delta t is much larger than this time scale tau, right? In physics 0 doesn't mean anything, right? It's just some with respect to something, no? So it's always in the which scale you are looking at, right? So this delta t time scale goes to 0 mean you are looking at a time scale delta t which is much larger than this time scale tau. So in this case, if you are interested in a time scale which is much larger than this tau, you are only going to measure things. You have a clock, you are going to measure the position which is much larger with accuracy which is with a time which is much accuracy which is much larger than this tau, then you can drop this term here, because it's like as if you are taking tau going to 0 limit, right? So this is equivalent to taking the tau going to 0 limit. So that's the meaning of the Overdamped equation, right? See, it is not impossible to measure things nowadays. So this is what I am going to do. What is this tau? How much is a tau? What will be the value of tau? Any guess? So tau you can actually compute. So this is, let me just give you a homework problem. So what is the tau? Equal to m by gamma. So you know, so what is the dimension of this particle? R is about 1 micron, right? So then to calculate the mass, what else do you need? If you know the dimension of the particle, to calculate the mass, what else do you need? Density. What do you think about the density? How much will be the density of this colloidal particle? D? Can you guess? This colloidal particle is in water, right? You are measuring the colloidal particle in water. Huh? Sorry? If it is less than water, what will happen? Will it float? It will come up. If it is heavier than water, so the density of the particle must be of the order of water, right? So density of the colloidal particle is density of water. What is the density of water? Okay, so 1 gram per cc. So you know the density of water. What about this gamma? You know 6. What is gamma? 6 pi eta r. So eta is what? How much is eta? So eta is of the order of 3. Is it correct or no? I think it's correct. Right? So forget about all the factor. And what is this one? What is Pascal? Right? So now we can calculate everything. Do you need anything else? No. So if you put everything and calculate, so tau will be of the order of, what is the guess? Huh? 10 to the power minus 8. Okay, I think it's, yeah, okay. So 10 to, let's say, 100 nanoseconds. So yeah, it's more or less correct, yeah, right? So if you are looking at a time scale which is larger than this, depending on the values you put or this thing, it will be somewhere in between that, depending on the values you put. So if you are looking at a time scale which is larger than this, so what you will see is the diffusion, right? So you will not see this ballistic thing, and in that time scale you can actually remove this term. So in fact nowadays it is possible to do experiment in that time scale, right? I think last year or last year there was a Nature paper. So they have actually looked at the time scale which is of this order, and you see ballistic motion, right? So how much the particle will diffuse? So you can also calculate the diffusion coefficient. So diffusion coefficient will be about, let's say, yeah, I don't know. So this roughly, it might be 1, it might be it might go up by a factor of 10, or it might go down by a factor of 10, up to that one, right? So if it is a diffusion coefficient, how much the particle will move in 1 microsecond? So if you see that if it is the thing, so then this delta x square, average square of this, so this will be about 1 nanometer in 1 microsecond and about 1 micrometer about in 1 second, right? So if you look at an ordinary microscope which has a resolution of micron size, right? So you will not see this movement, right? So only you will see. So this is so the reason it was in a Nature paper, because it is going to a low resolution in time as well as low resolution in space, right? Because if you are looking again, it's like a nanometer resolution or like a micrometer, right? So if you go to that small time scale, then only you will see this ballistic one, and in all these other time scale you can remove this factor, right? So this is the meaning of overdamped equation. So now let me just I have 5 minutes. Let me just derive the general Fokker-Planck equation for a general Markov system. So what is a Markov system now? What is a Markov process? So you know what is a Markov process now, right? So Markov process is basically probability of the process at some instant is just given by the previous instant, right? So let's call this variable y, so which has y1, y2, yn, right? So it's a process of n variables, right? It's a Markov process, means this variable they satisfy a linear stochastic differential equation, right? It has to be linear because this process equal to noise. Is it a Markov process? It is not Markov process because x at time t, it depends on 2 previous time steps, right? So it's a non-Markovian process, but it still can be made Markov if you go to one higher dimension. If you define a velocity, right? So this can be made. So only x variable is not Markov, but it can be make Markov. Any higher derivative process you can go to a Markov by taking sufficient derivative, right. So, this is if you define dx dt is equal to v, dv dt is equal to noise. So, this is a Markov process in x and v, right. So, similarly I have this variable y1, y2, y3, yn. So, one may be x, one might be v and so on, right. See, you have to look at so whatever it was there on the board, right. So, you have to look at in the time scales. What time scales you are looking the problem, right. So, if you are looking at a larger time scale which is larger than m by gamma, right. So, you are saying that if gamma is small, m by gamma will be large, but if you are looking at a time scale which is larger than m by gamma, it will be there, right. So, even this other one you can make it Markovian by introduce another variable called velocity, right. It is a two derivative thing, but if you write down in velocity and position, it will become a Markovian process, right. Okay. So, now this I have this one. So, you are interested in p of y at time t. So, I will just follow the steps as before. So, what was the step? T plus delta t is equal to p y t, right. So, this is the probability that it was at y at time t. Right, it was at y minus delta y at time t. Then the probability density for the jump, that it jumps in delta t time delta y, right. But now it jumps from where? It jumps from y minus delta y, right. So, it can be a function of this variable also. So, I am now assuming that this is not a function of time, right, but it is only a function of space, right. So, I do not have any time dependent force times d times delta y. So, I will do the same thing as Taylor series expansion as before, but now what is my variables or what is my function? This is my function, right. So, this function is g of y minus delta y. So, I know what is the Taylor series. So, Taylor series is g of y minus delta y del g del y plus delta y square by 2 del 2g del y square plus, right. This is what I have. So, I put it here again. So, what do you get? So, this left hand side I will do whatever I have done before. So, I am not going to write on the left hand side, right. So, what is the first term? So, what is g of y? G is p times phi. Y is my, okay, so this basically, yeah, so I should, what I should put, so in fact, yeah, so delta yi del g del yi goes from 1 to n plus I equal to 1 to n, j equal to 1 to n half delta yi delta yj del 2g del yi del yj plus the, right. So, y is, okay, sorry, so y is this one, so it will be like a, right. So, this will with respect to all variables, right. This is a Taylor series expansion if you have many variables, right. So, now what about the first one? First one is p of y times phi of y and then this one, right? So G is what? G of y is P of, right? So this is, let's write down P of y t phi of delta y y d of delta y. So this is the first term, right? So G of, so this is the definition of G at y minus delta y. So G of y is basically replacing this that whatever thing for y, right? Second term, I have minus infinity plus infinity minus I equal to 1 to n delta yi del yi of p at y phi delta y y d of delta y, right? Because z is this one. So similarly third term, so third term is half sum over I sum over j. So I have this integral, then delta yi delta yj del 2 del y1 I del yj p y phi delta y y plus this other terms. These other terms will go to 0 by the same arguments I have been using earlier, right? So I am not going to even say. So now see, this integral is with respect to this variable delta y, right? So I can take this integral sign outside, this p of y will come out, and integral over this phi is just 1, right? It's just a normalization of phi. So therefore this first term just gives me p of y, yt. Whatever the second term, so second term I equal to 1 to n, right? This integral is over delta y, right? This differentiation is over y. These are independent variables, right? Delta y and y they are independent variables. So I can exchange the order. So if I exchange the order, this integral will go inside. When the integral go inside, I have to also take this thing inside. So this delta y I can take it inside. As far as this guy is concerned, this is like a constant, right? So this I can just take it inside. So what I have is del yi, right? Then this y comes here. This integral comes here. This integral goes through p of y, right? Because y and delta y, these are independent variables. So what I have is integral over delta y inside the differentiation, right? Because this phi is still a function of y, so phi I cannot take it out, right? So what we have is delta yi expectation value times p of y, right? This is what you have. Similarly, right? So this gives me delta yi delta yj, I take it inside, do the integral. So that gives me delta yi delta yj and then p plus higher order terms. And now I can take this thing that side and divide it by delta t, take the limit delta t going to 0. So what is the equation I get? So I get this equation, del p del t is equal to minus 1 to n, right? Del yi delta yi problem to derive the Fokker-Planck equation for a overdamped Brownian particle in an external field. So, what is the equation? So, derive the Fokker-Planck equation for dx dt is equal to f of x gamma plus square root of 2d times eta t, right. So, for this one, so you know how to discretize, right. I have told you how to discretize this equation when this term was not there. So, now you can discretize even this term is there, right, otherwise I will do it in the tutorial, and where eta t prime is equal to delta t minus t prime, right. So, derive the Fokker-Planck equation for this one, okay. Yeah. So, this one, okay, if you try to derive, otherwise we will do it in tutorial. So, I was supposed to do some other stuff, but anyway it is the end of the lectures, maybe tutorial will do. There is something called the survival probability, right, which is very important. So, maybe I will just going to tell something about the survival probability and the first spaces probabilities for Brownian motion. So, today's tutorial. Yeah. Okay. So, if there is some question I can answer, otherwise we will just wait for the tutorial.